Today's lesson is all about chemical bonding. There are two types of compounds in our lesson for today, which are ionic and covalent compounds. Now let's begin with these two examples, sodium and chlorine. The electron configurations of the two are as follows. Their shell diagram are also drawn on the board. Now, what I want you to focus are the electrons on the outermost shell of each atom. Sodium has one electron on its outermost shell, meaning to say it has one valence electron. Chlorine on its outermost shell has 7 electrons, meaning to say it has 7 valence electrons. Which of the two atoms is stable? According to the octet rule, an atom becomes stable if it has 8 valence electrons, hence the name octet rule. Now, which of these two atoms were able to satisfy the octet rule? If your answer is neither of them, you're correct. Neither of the two atoms were able to satisfy the octet rule. Why? Let's observe. Since sodium has only one valence electron, it lacks 7 more electrons to become stable. While chlorine having only 7 valence electrons, it needs one more to become stable. When these two atoms meet, they can perform something that will make them stable. That is what we will observe in the next part of this video. Now, sodium has only one valence electron. It can perform or it can choose between the two options. Option number 1, it can look for 7 more electrons, which is a bit difficult. On the other hand, it can simply give off all its valence electrons. Well, it has only one valence electron. And when that happens, take a look. The outermost shell doesn't anymore have any electron at all. We can disregard that, and as you can see, the second shell becomes the outermost shell, and that shell has 8 valence electrons. So sodium was able to reach stability by releasing or by losing its valence electron. Now, when sodium loses an electron, it becomes a cation with a charge of positive. What about for chlorine? Chlorine has only 7 valence electrons. So it means it needs to look for one more electron to become stable. And where do you think that electron be coming from? Well, it's too obvious in the diagram, right? The electron that was given off by sodium will be absorbed or will be gained by chlorine. And when that happens, your chlorine now has 8 valence electrons satisfying the octet rule. Now, if sodium, who lost an electron, becomes positive, what about chlorine, which gained an electron? Did you say an ion? Correct. When chlorine gained an electron, it became an anion, negative. Now, when you have a positive and when you have a negative, what will happen to them? They bond to one another, forming the compound NaCl. And that is how ionic bonding occurs. It happens when you have a metal and you have a non-metal. They bond together, forming a compound, ionic bonding. So we now have the compound NaCl. How do we name it? We use the formula cation plus anion. So we name the metal cation and we name the non-metal plus the suffix IDE. Let me give an example. For Na, the name of the Na element is sodium, while the Cl, which is your chlorine, plus the IDE becomes chloride. Hence the name sodium chloride. Now let me now show you the other names of the anions. For carbon, when it becomes an anion, it's called carbide. Nitrogen is nitride. Oxygen is oxide, and so on and so forth. Please remember that one because we will use this list later on. Again, this IDE suffix is only applicable for non-metals. For metals, their name is as is. Okay? Now, let's try some examples. How do we name LiF? So, we use again the formula, cation and anion. Li is lithium, and F fluorine, it is fluoride. So the name is lithium fluoride. Next one. What about the ionic compound Mg3P2? So what is the name of our metal, the Mg? And what is the name of our anion P? Magnesium plus phosphide. So the name is magnesium phosphide. Next one. What about the ionic compound AlCl3? What is the name of our Al? And what is the name of our Cl? Did you say aluminum and then chloride? You're correct. And when we combine these two names together, we have aluminum chloride. So that is the rule of naming ionic compounds. Okay? Ionic compound is one is metal, the other is non-metal. Now, what about if we have this scenario? We have two elements, carbon and oxygen. Now, if you're going to browse your periodic table of elements, you will see that these two elements are both non-metals. So that means we can no longer apply the ionic bonding principle because, well, in ionic bonding, one should be metal, the other is non-metal. Here we have two non-metals. Now, their electron configurations are as follows, while their shell diagrams are as follows. Now, which of the two were able to satisfy the octet rule? None. Okay? So carbon has only 4 valence electrons here, while your oxygen has only 6 valence electrons. So neither of them was able to satisfy the octet rule. If you notice a while ago in the ionic bonding, the metal is the one that gave the electron, while the non-metal was the one who gained an electron. That's basically the property of the two. Metals tend to give off their electrons, while the non-metals tend to gain their electrons. Now, since these two elements are both non-metals, it means to say both of them will gain electrons. If that is the case, well, how can they attain stability if no one will give its electron? There is another possible way. Take a look. Your carbon has 4 valence electrons. Your oxygen has 6 valence electrons. Since none of them want to give their valence electrons, what they can simply do is to share their electrons. And that is the key word for this type of bonding, sharing. Okay? So, carbon can share 4 of its valence electrons. Oxygen can share 6 of its valence electrons. Take a look at the next step. Carbon can share 4, but oxygen just need 2 more to become stable because it has already 6 valence electrons, so it just needs to have 2 more electrons. That means carbon will only share 2 out of the four. Okay, out of the four valence electrons, it will only share two. Why? Again, because oxygen just need two more. So how do we count this one? Take a look. For oxygen, it has 1, 2, 3, 4, 5, 6, plus the two shared, 7 and 8. Oxygen was able to attain stability. But what about your element carbon? Let's count. 1, 2, follow the line, 3, 4, plus the shared, 5, 6. It's not yet stable. So how do we solve this one? We can do this by adding another oxygen. Okay? Oxygen needs two more electrons, right? This carbon here was able to already shared two of its four valence electrons. It has still remaining two valence electrons, which is what our oxygen actually needs to become stable. 1, 2, 3, 4, 5, 6 plus the 2, 7 and 8. Our second oxygen is already stable. What about our carbon? Let's try it again. Follow the outermost shell. 1, 2, 3, 4, 5, 6 from the first oxygen, 7, 8 from the second oxygen. Carbon was able to attain stability. Now, how many carbon did we use in this diagram? We used 1. What about for oxygen? How many oxygen atoms did we use for this diagram? 2. Hence, we form the compound CO2. 1 carbon and 2 oxygen atoms. Okay? And that is possible because these non-metals shared their electrons. So how do we name the compound CO2? We use this formula. Prefix nonmetal plus prefix nonmetal IDE. Sounds confusing? Let's try. So what is the name of our first non-metal? Carbon. What is the name of our second non-metal? Oxygen. But what do we call oxygen with IDE from the previous one? Oxide. Now, what about these prefixes? These prefixes are these prefixes. And to determine which of these prefixes will you be using, you just simply look at their subscripts. Now, what is a subscript of our carbon? We don't see anything, right? That means 1. What about for oxygen? What's a subscript? 2. Okay, so carbon has 1. That means the prefix is mono. While oxygen has the subscript 2. That means the prefix is di. So to write that, we have this. Monocarbon plus dioxide. So we have the prefix mono for the 1 subscript and the carbon, the non-metal. Then we have the prefix di, since oxygen has 2. The non-metal IDE of oxygen is oxide. So monocarbon dioxide. But there is a rule to follow for the prefix mono. The prefix mono is only for the second non-metal. That means the first non-metal will never have the prefix mono. That is why instead of monocarbon dioxide, we have carbon dioxide. You combine these two names together, and the name of our compound is carbon dioxide. Next one, P2O5. Okay, again, the formula is prefix nonmetal, prefix nonmetal IDE. Now, what is the prefix for the first element? phosphorus. Okay, that's di. Next, what about the prefix for the second nonmetal, which is the oxygen? Penta. Okay, so we use these names: diphosphorus pentoxide. Notice that I dropped the A from the penta. If you have an oxygen and the prefix ends with A, just like penta, you drop the letter A. You combine these two names together, you have diphosphorus pentoxide. Okay, next one. Let's try this. CCl4. What is the name together with the prefix of the first nonmetal? Correct. That's your monocarbon. What about the second nonmetal with the prefix? Correct. Tetrachloride. Okay? But don't forget, the prefix mono is only for the second nonmetal. So we drop the mono, we have carbon tetrachloride. Combine the two. We have carbon tetrachloride. Okay, last one. We have, no, that's not no. Okay, it's NO. You don't read it as no. Okay, so what is the name of this compound? NO. What's the prefix for the first non-metal together with its name? Mononitrogen. What about the second non-metal with the prefix? Monooxide. Okay, so we have nitrogen monoxide. But if there is a prefix mono for the first element, we drop it. So we have nitrogen monoxide. Okay, the compound's name is nitrogen monoxide. Well, you don't write monooxide. Okay, so if that happens when you have two consecutive O's, just drop the second O. Okay, so we have nitrogen monoxide. So to summarize everything, let's have this table. We have here the ionic compound and the covalent compound and their properties. So for ionic compound, the mode of bonding is through the transfer of electrons. The metal gives the electron or electrons, while the non-metal receives or gains the electron. While for covalent compounds, the valence electrons are shared. For ionic compounds, the compositions are metal and non-metal. For covalent compounds, all of them are non-metals. So again, if you have a compound and you see a metal, that's ionic compound. But if you see the compound with only non-metals within it, that is a covalent compound. And so to name them, we use this formula. For ionic compounds, we name them with the cation name and the anion name. While for covalent compounds, we use the prefixes. So the bottom line is, if it's ionic, no prefixes. But if it's covalent, prefixes. So that's it for the lesson for today. I hope you were able to understand how ionic and covalent compounds are formed and how we name them. Thank you for watching and God bless you.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.